I was like 4 minutes ago being interviewed by the head of the Dutch Supreme Court and talking to literally all the lawyers of the Netherlands for 45 minutes about something I really didn't know very much about. It was highly stressful, and I just got here. And this is about extreme weather, which is easier. So I'm out of breath. It was actually, I got a little exercise getting over here. It's good. Okay. This is actually interesting because this subject is responsible for a lot of the legal activity that is going on inside the United States and around the world. So it's actually a tie-in with why I'm out of breath right now. I don't know if stop me if I've told you this story before, because it's an occupational hazard of being 62. So if I ever tell you a story you've already heard, somebody say, "You've already heard." So this summer, a bunch of us started a school for judges. There's an organization whose job it is to continue with the education of U.S. judges, the judiciary. And this includes the Supreme Court and the appellate courts and so on. And the first one was with the appellate courts. And so did I tell you this story? Yes? Some say yes, some say no. Some of you don't pay attention. The ones who said yes have been paying attention. Okay, the bottom line here is that our judiciary is currently swamped by courses. See? Now you all paid attention. Okay. I should have been a clicker question because you would all gotten an A. Okay. Except for me. So the thing is that we're swamped because the public can say that this event that knocked my house down, that you should have protected me from, was in part caused by climate change. Now, it wasn't very long ago, like 3 years ago, that the most common thing you read about when it came to extreme weather and climate change was that you cannot, this is a quote, attribute any individual event to climate change. Who's heard that? Who remembers hearing that? It was super common. And it turns out that is now false in a big way. And it's the change, the scientific change, that has in fact caused a lot of this avalanche of legal activity. I can remember when we first decided that this was false and had gathered lots of evidence that it was false and actually worked to make it false. And Michael Oppenheimer, who knows Michael, who's a professor in the Woodrow Wilson School, and I went down to see Obama and said, because he was saying this all the time, right? And he never said it again, okay? So it actually worked, okay? But, so anyway, which is what we're talking about here right now. So I want to talk about extreme weather, and it's because it's events like this one that make the climate change in the here and now real. It's not the mean temperature that hurts you. It's the extremes of weather that hurt you. And one might think that a change in the temperature of 1 degree Celsius, or a better scale is 1 degree Kelvin, right? Because that's, so space is close to 0 Kelvin, and we're 270 degrees. One part in that 270, you might think would make a small change in extreme weather. But because of interesting physics and interesting mathematics, that little change can be the 1,000-fold frequency or more in the extreme weather frequencies. The tails get amplified. And what we always had wrong was that we required so much data to be able to demonstrate that 1 degree Kelvin temperature change. It's a tiny change, you need a lot of data, we got it. We thought we needed a similar amount of data on extreme weather events, but they're rare. So you can't get the data. Sample size is too small. Turns out, though, the delta, the change you're looking for, is so huge. The small sample still gives it to you, okay? That's interesting. So we're going to talk about all this stuff. And yeah, there's an outline. Okay, now, climate is technically the probabilistic distribution of the weather. The difference between weather and climate is that climate is the probabilistic distribution of weather events that can be thought of as random or stochastic. So like if you're rolling a dice repeatedly, any one outcome is a probabilistic event. You can get a 1, 2, 3, 4, 5, or 6. But if you roll the die a lot of times, then the distributions of 1, 2, 3, 4, 5s, and 6s better look like that, or the person who's giving you the die gets shot or something, right? Because it's loaded, all right? So this is the climate of the die. And that particular outcome is the weather of the die. Now, is weather really random? Well, this is actually complicated, and not just, and not complicated for the usual reason. It's not scientifically complicated, it's conceptually complicated. The weather is demonstrably chaotic. And a chaotic but deterministic process is one in which any tiny change in the initial condition will affect subsequent events a lot. So the classic example is the butterfly effect. You can't predict next month's weather accurately in New York, not because the climate is really random, but because a butterfly flapping its wings in Beijing is enough to change next month's weather in New York. It's enough of a different initial condition. And so different nearby initial conditions diverge from one another, and you simply can never know the initial condition well enough to be able to predict beyond a certain time horizon. And so and moreover, there's a theorem that for any truly random process, a sequence of random events that are really random, meaning that if you start from the same initial condition, you get different answers when you do it differently. In a chaotic process, if you start exactly with the right initial condition, always the same thing will happen, okay? But if tiny difference in the initial condition, and it just diverges all over the place. For every random sequence that is finitely long of data, there exists a deterministic process that is chaotic, that is indistinguishable with finite data. So you cannot know. There is no practical difference, okay? See, so it's interesting. All right, so climate is the probabilistic distribution of the weather. And when somebody who's a contrarian says, we can't predict the weather, so we can't predict the climate, that's kind of crazy, right? Because the distribution of the weather could be highly characterizable, even though any one event is uncertain. Okay, so the attribution of mean climate change has been something that was developed and is widely accepted now. The methodology for doing this was developed during the 1990s, and it took about a decade to socialize this methodology within the scientific community until they all thought, yeah, this is okay. And this may sound weird, but you have to remember that scientists are busy people too. And the science is fragmented. So there was a group working on this methodology to attribute formally climate change to, for instance, fossil emissions. And they developed the methodology, argued about it, and compared it and tried different methods out on the same data, and eventually coalesced around robust methods. Didn't matter how you do it, you always got the same answer, okay? And then they became convinced as a community, and that has to sort of bleed off to the rest of the community who aren't specialists in this. That took about 10 years' time. And the main way of doing things, you can do it with weather or with data, but it is possible here, in this case done with a model, or a whole collection of models. This is all the climate models of the world, including those that are empirical or are based on data. And if you take out the fossil emissions and just have the volcanic forcing and the solar forcing and all the other forces, the set of predictions together with the within and between model uncertainty is given by those blue lines. This is time going up to 2020 on the horizontal axis, and that is 1880. And this is temperature change going up to 2 degrees. That's zero being by definition where we started. So 0 is the difference from where we started, okay? And what you can see is that the model, that none of that effort, none of that physics would have predicted, even given the uncertainty, a big temperature change. And yet, in fact, that's exactly what we observed with the uncertainty, both within and between methods, given by the sort of amber-colored band there. And the red is the mean of all the analysis. That's the best guess. And the black is the data, okay? The black's the data. And the data subsequently has spiked up. And so it's right on top of the red. This is just the land surface where you can see the climate change is larger. The oceanic surface where it lags behind because the ocean is constantly bringing up cold pre-industrial water, right, in that thermal overturning, whereas the land is closer. And then these are the individual continents. And you can see that as you get to smaller areas, there starts to be some blurring between the blue uncertainty, that is the no greenhouse gas forcing uncertainty, and the red uncertainty. And so the attribution of the observed climate change to fossil emissions, which are included in these analyses, but not in these analyses, the attribution becomes weaker as, you know, even by random chance, you might not be able to tell the difference. And because it was thought that in going from the globe to continents and then subcontinents, you're sort of losing enough data to get the signal, it was thought we're never going to get extreme events. So it was impossible to attribute any one individual event to climate change. Right? So any questions about this? Okay. So yeah, the red has fossil emissions in it, and the blue doesn't. And then there's a difference, and the red looks like the data, whereas the blue doesn't. It's pretty simple. Okay, now you read all the time, it's possible to attribute some individual extreme weather events to anthropogenic change. If you read the newspaper, you hear about this all the time. There are already rapid attribution analyses that have attributed to the latest heavy rainfall in Texas, which just happened, to fossil emissions. All right, that's already happened. These analyses are being run real time. There's an organization just across the street here at 1 Palmer Square that has just finished building an automaton that monitors the weather in the United States every day and does a forecast attribution. It's forecasted to be 94 degrees tomorrow. The attribution analysis says that 4 of those degrees are brought to you courtesy of fossil emissions, and it's going to damage your corn crop, like that, okay? And so this, and it looks like, so that analysis already shows that 4 of every 7 days in a week in the American South have attributable heat already, okay? So this really has changed very, very rapidly. So this is about changes in extremes. And so this is a distribution. And remember, climate is a probabilistic distribution of weather. And so the probabilistic distribution that almost everyone knows about is the Gaussian or normal distribution, the so-called bell-shaped curve. What you may not know is why the bell-shaped curve is so ubiquitous. And it turns out it's for a pretty simple reason. If you take any set of random numbers that are what's known as, that aren't completely dependent on one another. In other words, you can't, by choosing one, fix the value of the next one, right? It has to be some degree of wiggle between the numbers. Then if you take any sequence of those numbers, driven by any probabilistic distribution whatsoever, then the sum of those numbers, as the sum becomes a large sum, that is, a large number of individual independent events, so 10 or 11 or 12 things you're summing together, then the distribution of the sum goes to this Gaussian distribution. And not just something that looks particularly bell-shaped, but an actual mathematical limit. And I'm just going to say this to show you how special it is. It's 1 over the square root of 2 pi sigma times the quantity e to the minus brackets x minus mu squared all over 2 sigma squared. Okay? All of that stuff comes inevitably from any random process that's got a bunch of independent events you sum together. It's like, how's that possible? It's like weird, right? Mathematics is beautiful in that way. And so the point is that all of our intuition about statistics, because that was the sort of most robust result, comes from these normal distributions. And we'll talk about why extreme weather is different in just a minute. So what happens when you change, how do you change the extremes? Well, if the mean shifts, right, from here to here, then you can see that the frequency of extreme shifts. Now it shifts, but not that much. Changes some, but not that much. So the frequency of extremes is sort of the red bits in the tail. The area of the dark red bit is extreme heat. You could, in principle, also have this distribution changing to this one, which is increased variability, but no change in the mean. And that would also change the extremes. Not a lot of evidence that this is going on, quite a bit of evidence that this is going on. And there's also the possibility of changed symmetry, so that the distribution could shift from being more symmetric to skewed in a particular way that would thicken the tail. Those are the 3 ways that it could happen. Now, I want to see. Yeah, I'm going to actually say something that isn't in these curves now. Yada, yada, yeah. So I'm just going to say this, and I'm not going to test you on this, so just pay attention. The thing is that the way that these Gaussian curves work is by summing a bunch of independent events. Now think about temperature. The funny thing about temperature, the physics of temperature on the surface of the world, is let's suppose that as an event becomes more and more extreme, like as we add hot sort of tendencies together in a place and a place gets super hot, the thing is that the subsequent events start to be determined by the current state. And it's because the wind blows between hot and cold areas. As a particular place in the world heats up, the wind wants to blow from the hot to the adjacent colder places, and that mixes up the air and tends to cool it down. And what that does is it makes unlikely the most extreme extremes. So in the United States, we've seen 140 degrees Fahrenheit places, but we've never seen 150. And 140 is not that uncommon in some parts of the Middle East. And so so from a Gaussian distribution, we would think we should see all of these extremes, but rarer and rarer. And the fact is that the physics clips the tail. Now what happens is that when the mean changes a little bit, the clipped tail actually moves into new territory that you've never seen before and creates events that couldn't have happened before. And that's why the intuition from a Gaussian distribution isn't so good. If you look at the weather event a couple of years ago that killed 90% of the barrier reef and ask, how likely was it before fossil emissions were in the atmosphere? The analysis came back essentially impossible, okay? Even though the climate has only changed a little bit on average. And for exactly that reason. Okay, now there are two types of extremes that we can talk about. We can talk about the frequency or the severity. So for any event, like here, This thing is the probability of occurrence. It's the frequency. And what the tallness of the bell-shaped curve here means is this kind of an event is more frequent than this kind of an event or this kind of event where the curve is shorter. So that's the frequency. The severity is along the horizontal axis. So that what that shows is that really cold events are infrequent, average days are more frequent, and really warm events are also infrequent. Whoops, going the wrong way here. So we can talk about the frequency of an event of a given severity. We can say, oh, you know, a 90-degree day. How common is it today, this year, relative to how it was, say, when you were born? Right? So is it more frequent than it was in the past? And so, for example, is a 90-degree day happen once every 2 weeks in the summer as opposed to once a month? That would be a doubling of the frequency. We can also talk about the severity. How hot or cold or hot or how much precipitation occurs or the driest summer or the highest wind speed in Y years. You could freeze the frequency, right, and look at the change in severity. So that, for instance, let's suppose that we take when your parents were children and they're lying in bed, say you come from North Carolina, it's North Carolina, and they don't have air conditioning, and you're thinking about the hottest night in 20 years, all right? The severity of that night, how hot was it? Let's suppose it's 94 degrees for a low during the middle of the night. And then you ask yourself, that warmest night in 20 years, today, how hot is it? And the answer might be 98 degrees, all right? So that's the same frequency and how much there's been a change in severity, all right? So because there's both frequency and severity, when we talk about a change in extremes, it's really a two-dimensional thing, and the way people get their heads around it is to freeze one and talk about the other, right? Same frequency, different severity, same severity, change in frequency, okay? So there's a statistic that is originally due to this guy named Miles Allen, who's a clever guy at Oxford. And he wrote it down in 2003, and it turns out it's not a novel concept at all. It's what epidemiologists used to assess fractional risk. When somebody says weather is complicated and is affected by many different things, well, so what? The question is, how much did fossil emissions increase our risk of an event like that? It's a probabilistic notion of causality. So let's suppose this is the distribution of temperature, the maximum daily temperature in some period in the pre-industrial, and let's suppose this is the distribution for the current climate. The blue arrow is the probability that a maximum daily, see, so this blue arrow here, which is over 40 degrees Celsius, and then that gives us the probability of that event. See that? That axis is the probability or frequency, 1 over the frequency of that event. And so it's unlikely in the pre-industrial, and it occurs, if you could read this thing, about 2, in this case, days in 1,000, all right? 2 days in 1,000 in the pre-industrial. And so that number we're going to call P40, the probability that the maximum daily exceeds 40 degrees Celsius in the pre-industrial. Got it? All right. The orange arrow now shows the 40-degree probability, the height of the curves at 40 degrees today. And you can see it's 6 parts in 1,000, not 2 parts in 1,000. It's 3 times more likely than it was in the pre-industrial. So the fraction of attributable risk is just 1 minus P40 for the pre-industrial divided by P40 for today. And that turns out to be 0.67. If you experience a 40-degree temperature today, since it's 3 times more likely to have occurred today than it was in the pre-industrial, there are 2 chances in 3, or 0.67, that negative experience you're having was due to climate change, all right? because 2 of 3 days like that now are due to climate change. So it's a very simple concept. It's the fraction of attributable risk. Now, does anybody have any objection with that as a notion of causality? Well, you're all going to be silent on this, and it's wise because it's actually complicated, right? So you know, we're used to thinking of causality in mechanical terms. There's a trial. Somebody's dead. And did so-and-so pull the trigger on the gun that shot them or not? It's a very mechanical notion of causality. But let me give you another kind of a trial. A person is driving at the legal limit, and somebody's walking across the street and they run them down. And you're on trial for manslaughter because you knowingly drank to the legal limit. And you ran this person down. Now, that's not so clear-cut. Nobody can trace the ethanol molecule in the person's brain, the driver's brain, and whether or not it impacted his or her reaction time in moving the right foot from the pedal to the brake, right? What we know is that driving at the legal limit made that accident 20 times more likely. So there are 19 times chances in 20. The FAR, fraction of attributable risk, is 0.95. The legal definition of causality is that if you've increased the probability of an event in the United States by a factor of 2, made it twice as likely, then that's like pulling the trigger, okay? So this is actually complicated because who knew that in our lives, many of our notions of causality are actually statistical thresholds, not sort of mechanical events, all right? So this fraction of attributable risk, when you say climate change has caused something by this metric, you're doing what we do in all kinds of aspects of our lives. That person's drinking caused the death of this pedestrian. There were many things that caused the death of the pedestrian. There could have been a street light where the person was and there wasn't. The character could have changed his tires and didn't. There could have been a pothole in the road, you know. Instead of being a pothole, it could have been all kinds of things contributed to the accident. But the legal definition is that if you've increased the risk enough, that's it, okay? The same thing goes here. And this is why, in fact, there have been an explosion of cases. Turns out you can make statistical statements about how frequent events have become relative to the past because of fossil emissions. Those probabilistic statements, which are really statements about the change in the distribution of weather in the tails, right? Which are climatological statements, and yet they're causal statements by a legal definition about weather, which are single individual events, okay? It's a relatively subtle set of concepts, but that's what makes it interesting. Okay, fraction of attributable magnitude, same thing. Here we've got an event that occurs at the frequency of 0.009, or once in 1,095 days, or once in 3 years. That's what this event is. Okay, once in 3 years in the pre-industrial. And how hot is that event? Well, that event is that hot. It's 39 degrees Celsius, okay? So that height equals once in 3 years. And where it crosses, right, that occurs at 39 degrees Celsius. So call that M3 in the pre-industrial, 39 degrees Celsius. The magnitude of an event occurring once in 3 years today occurs right there. That's the once in 3 years probability. The orange curve is that high at, 45 degrees Celsius. Okay, so that's M3 today, 45 degrees Celsius. And the fraction of attributable magnitude for a temperature greater than 45 degrees is this quantity here, which is about 13%, okay? If M3 is 39 pre and 45 today, then the fraction of attributable magnitude is 13%. 13% of this extreme that you just experienced, 13% of it is actually been brought to you by the change in the shape of the distribution. See how that works? All right. So that's an equivalent kind of a concept. And it actually takes a while to wrestle with these. These formulae are easy to write down, and they're relatively easy to manipulate them if you stare at them. Even if you're not a good math person, you can do this. But it's worth thinking hard about it because the concepts behind them are actually subtle, even though we use them all the time. So the fraction of attributable risk and the fraction of attributable magnitude can be defined over many periods. We had the pre and post-industrial in that example, but we could do anything, right? We could do in the 1990s versus today, when you were a kid versus today, World War II versus today. Any period at all, you can compare the fraction of attributable magnitude or the fraction of attributable risk of the fossil emissions in that period. That also turns out to be critical for legal cases. If you're suing a fossil company, you want to know this collection of fossil companies, how much of the CO2 did they put in the atmosphere over the period in which they existed, right? Like that. And so how much of the climate change, in fact, is due to the stuff they've sold and that we bought. I want to say, all right, and that we bought. That's the interesting ethical problem. Okay, so statistical methods can be used to determine if the fraction of attributable risk or the fraction of attributable magnitude is significantly greater than 0. So given the statistical noise, is there enough data to actually say, yeah, the fraction of attributable risk when we calculate it is greater than 0, or it's so noisy I really can't tell, right? Might be 0, might be 0.1, yeah, you know, the best guess is 0.05, but I don't know. But if you can say it's statistically greater than 0, then you've detected a signature of the fossil emissions on the climate change. So there's a lot of words here. I don't know if I want to use them. So the FAR and the FAM can also be defined by climate models. So if you believe the model, and this is a big if, you can run the model many times to calculate the current distribution of extremes. You want to check the results against data to see that the model is up to the task. One can then do the same thing with the model run in a counterfactual world without added anthropogenic greenhouse gases and say how likely are the events in this counterfactual world without greenhouse gases, and then compute FAR and FAM for that for those sort of model-generated data. Okay? And this result, this kind of a result, is often called attribution. Now, this may sound squirrely, and there's a reason to think that it's squirrely. But the fact is that climate models have really gotten very good. They actually do predict observed distribution of changes everywhere in the world by close to 1%. And so legally, the use of models in this context has now started to gain significant ground. All right? That's the deal. And so being able to compute the FAR and the FAM, even for places where you don't have enough weather data or a long enough series of weather data, is now possible, at least in a legal context, although it still depends on the accuracy of models. Most of the time in this course, I'll say the results or the concern about climate change doesn't depend on the accuracy of models, but in this particular case, it does depend on the accuracy of models. Okay, so when was this first used? When was this technology first used? In particular, the data-driven and the model-driven calculations of fraction of attributable risks and fraction of attributable magnitude. And the first case was a paper published in Nature in 2004, the year after Miles Allen sort of wrote down the methodology. And the next year, they had a terrible heat wave in Europe. It killed something like 35,000 people. So how do you tell that? You look at hospital records and you say, how many people died during the heat wave? What were the causes of death? How many heat deaths do we usually have during a period like this? And the answer was plus 35,000 during this event. The upper bound on that estimate is, it could be as high as 70,000. In any case, it was a big deal, all right? It makes, 9/11 in the US, it's an order of magnitude smaller in terms of a morbidity event. And this has happened repeatedly. Europe just had another big morbidity event in the heat wave in this past summer. And so they were able to do this, and during the analysis, they could use both data because they had good temperature data going back to 1500, okay? And, you know, only in Europe. And it was the hottest summer ever since 1500. Okay, so it was really a rare event, right? And then you could also do it with models. And they concluded that the fraction of attributable risk was greater than 0.5, okay? Meaning that they concluded that the fossil emissions had at least doubled the probability of an event like this. Now notice that that's the threshold that would have tripped the US legal standard. Remember, if you've doubled the risk, you caused it, right? So that was the first case. There are a whole bunch of data in the IPCC, the latest IPCC AR5. And one of the best examples is for mild temperature extremes, where you really have lots of data. So I've just got this one little example here. This is from a figure in the IPCC. On the vertical axis, we have the return time in the 1990s for an extreme with a 20-year return time in the 1960s. Now, what does this mean? It means in the 1960s, it's the example I just gave you. In the 1960s, you're some person who was now old, then young, lying in bed, and you think, how hot is it? The hottest it's been in 20 years. How hot is it? Okay? So take an event of that hot, 94 degrees or something, and then say, during the 1990s, how hot was that 1 in 20 year event? And that's what's plotted on this vertical axis. Okay? So when one of these, if one of these bars were at 20, it would mean a once in 20 year event in the 1960s is the same heat as a once in 20 year event today, no climate change. If it's 1 in 10, it means it's actually colder than it was, right? And if it's higher, then it means that the frequency of those heat events has actually gone, the severity of those heat events has actually gone up. And so these are the data. That number is for the coldest nighttime low in 20 years, now occurs once every 38 years in the 1990s. That number means the coldest daytime high. That number means the hottest nighttime low in 20 years now occurs once every 8 years. Meaning if you're lying in bed and it's as hot as it was in the 1 in 20 year night in the 1960s, and you're lying in bed in the 1990s and you're at that temperature, there's a better than 1 in 2 chance that you're suffering because of climate change. Okay? Because it now occurs once every 8 years and it once used to occur once every 20 years. And that's the highest daytime high. Those are model estimates of the changes due solely to anthropogenic greenhouse gases and aerosols, which you can see looks just about just like the data, okay? The correspondence between the data. And so they have these for all kinds of continents all over the place, and they all look like this, all right? So for these mild extremes, we've got enough data to actually do this, at least at continental scales. Okay, so what I said before was that because physics draws in the extreme temperatures because the wind blows from hot to cold places and mixes up the atmosphere, the distribution of climates tends to have abrupt tails. They are literally, to use a mild pun, curtailed, okay, pulled in. And so that causes a small change in the mean to cause a big jump in the frequency. You see, if you take a vertical line right there, that's way higher than that because the thing is so abrupt at the tail. And that abruptness is caused by physics pulling in the tails. So extremes in this range have an FAR near 1 because they almost never occurred in the pre-industrial. There's substantial probability mass in the orange curve, but essentially none in the blue, which is almost at 0. And so this caused everybody to start doing this, and everybody realized, geez, the signals are so big, we have enough data to actually do this. And it led to a series of reports in the IPCC that established and reviewed this information, culminating in a National Academy of Sciences report on this that said, you know something, this is now ready to go. And that occurred in 2016. And so it's since that time, since 2016, that people in government have stopped saying you can't attribute an individual event to climate change, and in which the legal thing had taken off. The National Academy report said that we had good ways to attribute heat, coastal flooding, extreme precipitation, less so for winter storms, severe droughts, hurricanes, or tornadoes. That's now 3 years ago. Now, hurricanes have moved up a lot. Some severe droughts have moved up. Winter storms have moved up. Tornadoes are still lying back here in the weeds. Tornadoes are complicated, it turns out, because to make a tornado, you have to have heat that causes convection. You need cycling, big thunderheads, right? But you also need wind shear. There has to be shear in the atmosphere where one body of wind is moving fast relative to another body of wind, and that starts this thing rolling horizontally in the atmosphere. And what a tornado does is it takes that spinning thing and turns it vertical, okay? Now the shear decreases with fossil emissions, but the heat that causes the convection increases. So tornadoes are being tugged in two different ways, and we don't yet fully know which is the stronger, okay? All right, blah, blah, blah. There have also been, since 2011, there's now a 2018 one. They haven't released the 2019. There's a journal called the Bulletin of the American Meteorological Society that I'm sure is on everyone's nightstand. That has a special event a special issue every year at about this time that attributes the previous year's events or not to climate change. So it's actually worth reading. If you want to find out what experts have thought in the past was attributable to this, you can do so. There's a 2018 one, but there isn't a 2019 one. But we'll expect it. It should be out in the next 2 weeks or so. So 65% of the ones they've looked at have had a strong anthropogenic effect. But that means fully a third haven't. All right? It's not like they always find the signature. Sometimes, for instance, the thing that you thought was a terrible flood actually just seems terrible because of coastal development, not because the flood was actually the result of increased precipitation. Okay. So the weather does seem weird for a reason, all right? Because most of the events that we're seeing that are extreme are attributable. I've got some examples here. There was a tenfold increase in the frequency of heat waves, like the 2010 Moscow, or now 2003 European event. They've redone that. They now have fraction of attributable risks over 90%. 2010 Moscow event was really interesting because they thought they were going to have to evacuate Moscow. The fires had started as a result of the heat and dryness around Moscow, and the forest had caught. And then worse than that, they have all this organic matter. We talked about the fridge door effect in the far north, rotting the organic matter down there. Well, that organic matter had dried out and was burning, so that the ground was burning too. It was creating so much carbon monoxide that the air in Moscow was becoming toxic, and they thought it might become lethal. And they didn't know where these fires were. They couldn't find them. It's actually got quite a bit of remote territory. But it turned out the US called them up and said, believe it or not, we've got gizmos that look for heat signatures over Russia, right? Who could have guessed, right? Why would we have such a thing? So we told them where all the fires were, okay? So they could probably do that for us too. So anyway, that was a nice example of US-Russia cooperation. There's tons of these. 20x increase for the 2011 Texas drought. Lots and lots and lots and lots. So these go on. There's tons every year. You can look at the Bulletin of American Meteorological Society. Most sunny day flooding in the US now is attributable. This is just one example of how sunny day and coastal sunny day flooding events have happened. The orange ones are the ones caused by climate change. The blue ones are ones caused by putting a new road or something into some place, or the ground subsiding or something because of like pumping oil out of the ground, and so the ground sinks a little bit. So most of the events now are caused by climate change. 76% according to that analysis. This is one I showed you already before. 2016 aerial surveys showed that 96% of the coral bleached and died. The initial indication was that it was at least 175 times more likely because of fossil emissions. The main estimate was over 2,000. And the current estimate is that there was never an event like this back at least to the Pleistocene. And then during the Pleistocene, we don't have good records, but it was colder then, during interglacial and glacial eras. So there's tons of events. I'm running out of time here, so I'll just mention a couple more. Some of the analyses are now coming up with fraction of attributable risk of 1, and meaning it couldn't have happened without anthropogenic emissions. And this then takes the physical notion of causality and causes it to be equal to the statistical notion, okay? If the person pulled the trigger and if there's a probability 1 that they're the ones that shot the good person, that sort of thing. That's it, a couple of examples. These are actually both done here in Princeton. This is this big group. Tom Knutson is the person at our giant climate lab that's the NOAA facility co-located with Princeton that does this, and he's heavily involved in all this. A couple more slides and I'm out. Hurricane Harvey, fraction of attributable risk was 2/3, and the fraction of attributable magnitude was 15%, meaning 10 of Harvey's 45 inches of rainfall were caused by the fossil emissions, all right? And that 10 inches is a minority of the rainfall, but it's that last 10 inches really, it's the one that hurts you the most, right? Yeah, so this is a second analysis that said the fraction of attributable risk and magnitude is a little bit larger. It's another example. Arabian Sea hurricanes had never occurred before, and now they're starting to occur. And all of our analysis says that Persian Gulf hurricanes are now possible. The important point there is that all of the oil infrastructure in the Persian Gulf is not armored against hurricanes because they never happened historically. Expect one in your lifetime. Lawsuits filed, hundreds and hundreds of lawsuits filed all over the place. There's a new NGO that simply tracks all this. You can look at that website and find out what lawsuits are active and what they're doing about it, and what the evidence currently is. And those are the lecture teaching goals. So thanks a lot, people, and have a good weekend.